Okay, random access, you transmit at a full channel rate. In other words, you have the full channel to use. But you have no prior coordination between among the nodes. Between all the nodes, you don't have any coordination between them. You have two or more transmitting nodes simultaneously. That means you'll have a collision. You're starting to have collision, therefore you'll have a wastage. You need to have an error recovery strategy now. High detection and recovery from it. So you specify that the random access MAC protocol specifies that how to detect collisions, and that's the key question. Second, how to recover from collisions. Mainly it will be via delayed transmissions. Example of random access is slotted Aloha. Aloha 1, the pure one, a carrier sense multiplier access with collision detection and avoidance. Let's see the first one. Slotted Aloha. What are we assuming? First, all frames are the same size. Okay? The time divided into equal size of slots, i.e. time transmit one frame at the one time slot. Nodes start to transmit only at the beginning of that slot. So let's imagine this is how it is. That is your actual ring of the actual channel. Let's say it's divided into small slots as well, and you have a user to send. Each one of them can send one packet only, and that starts in the beginning of the slot. So let's say this is time 0, time 1, time 2, time 3. You can send that packet only at the beginning of that slot, and the other one can start sending at the beginning of the other one, depending when is that being sent. Nodes are synchronized. What does that mean? That means that you will know, all the nodes involved within the transmission know when the time slot starts. So if that's defined by time, 1 millisecond, 2, 3, whenever this starts, all nodes know that started now. So it's not like starting in the middle. It knows when to start sending. If two or more nodes transmit in the slots, all nodes detect a collision. For any reason, let's say 2 nodes transmitted at this time slot, a collision will occur. All nodes will know there is a collision here. So, how does it operate? The operation will be, one node obtains a fresh frame to transmit. If there is no collision, nodes can send a new frame in the next time slot. If a collision node happens, then a node will retransmit a frame each subsequent slot with a probability of P until a success. Let's see what does that mean. I'll show you here with this example. This will be very clear. Here you have 3 users, 1, 2, and 3, with 3 different colors. Each user trying to transmit at the 0 millisecond. You can see that. Both of them, or 3 of them, trying to send exactly at this time slot. Let's say this is T0, T1. And you have user number 1, user number 2, user number 3, all of them trying to send the same frame at that time slot. What will happen? Collision. So that will be defining a collision. So that means when the others can't send, they just wait. It's like flipping a coin. A user say, I will send if it's a hex. He waits a random time of seconds and he starts sending again. So in this example, time number 2, no one sent. Coincidence, no one sent. Went what? Empty. Became idle, so no one, it's a wastage as well. At the 3rd millisecond, user number 1 and 2 said we want to transmit, and a collision occurred again. What does that mean? Collision. No one can go through. When there's a collision, that frame don't get through. You need to retransmit again. They waited again for a few seconds. Number 2, send it afterwards. No one sent at the same time, which was successful. You see the pattern here? It's just waiting for a random amount of time, for p-probability of time, and then trying to send that frame again. People must say that, but what's the usability of this one? There is so many disadvantages. There are some advantages, but there are so many disadvantages as well. Eventually, all of you will go through. All of the 3 packets you try to send have been sent, but when? On the 10 millisecond or the 9 millisecond. So, what are the pros, what are the cons of those? The pros are single active node can continually transmit at a full rate of the channel. Fair enough. But collision will waste the slots as well. You have highly decentralized. Only slots in the nodes needs to be synchronized. And it's very simple. Yes, but it's wasted. Clock synchronized in idle slots, that's a cons as well. So that's how a random access works. That's how Aloha is called, slotted Aloha. Is that clear how it's working? Try to transmit. If there's a collision, you just wait for a probability time to send it. If it went through successfully, fair enough. If not, it waits for another amount of time to send it again. There will be a chance of collision, but a number of nodes will be able to send their packets with a full use of the rate of the channel. So what's the main advantage of this one? Anyway, compared to the channel partitioning one. What do you think? Main advantage. You're not wasting the channel when there is no one node. So in other words, you are using it in full. Is that right? But when there are two users trying to send at the same time, you'll have the wastage again, and there will be a collision. So it's not ideal, but at least you can use that full usability of the actual bandwidth. But it has so many issues with it. The probability of this going through is 37% only. There's a formula actually they counted for. You don't need to worry about the formula. It's just a matter of showing you that 37% chance you have to get that packet through. So it's not good, is it?
So could you just tell him the node then, just to keep transmitting and not waiting, just hold the whole thing?
But if everyone done the same, what happens?
Yeah.
You end up with all of them having that same collision. So it depends how greedy are you to try to send a lot. So in other words, if you are greedy and other ones try to think the same thing, no one will use the link. But again, this is how they, the beginning, tried to create it. That's 1971, the beginning. They tried to control it in that way. And afterwards they said, okay, let's create something better. They thought they're creating something better. They created something called the pure law. This one has a criteria or a characteristic where you need to send only at the beginning of the frame. So what does that mean? We just showed you that if this is your time, if this is your bandwidth, here is it, and it's divided by time frames because it's bounded by slots of time. And we send, you only can send at the beginning of that frame. So if this is T0, T1, you only can send at the beginning. This is how they worked it out. The pure aloha one doesn't follow that rule. It can send whenever it wants. So in other words, a T here sends a packet and it goes by to the other time slot. So you're sending it in the middle rather than the beginning. So you might have a frame sending this way, ending this way. So it will be more trickier in a sense because you're sending anytime you want, not at the beginning. The question is it better or worse? Why?
You disturb both.
So even if you manage to send one, you'll be disturbed by anyone sending it from the end of that time slot or the beginning of it. So the chance of this going through, it will be even worse than the actual one. The chance of it in reality is 18% only. So what did you do? To make it worse, they tried to make it better. They created a whole new dilemma of you can send whatever you want, but you end up collision with other nodes trying to send normally. So they did not fix the thing. They created more issues. Exactly what happened here. Everyone? So that's worse than the actual slotted law. They created something. They wanted to have something better. And this is last year question. Last year exam question of asking about the CSMA. What's that? That's carrier sends multiple access. You listen before you transmit. Let's read. And if channel is ideal, i.e. no one is using it, then by all means try to send. So what is the word listen? Let's relate this to human. To humans, if I ask you, if two people are trying to have a conversation, and one of them starts speaking, and the other one at the same time starts speaking, what happens? You stop, wait the other person to finish. Then you try speaking again, which is normal. Should be normal. So at the same time, you listen. If he's quiet, you start speaking with him. Fair enough. So that's similar to networking. The carrier sense, you try to listen to the network. If it's ideal, no one is using that spot, similar to this one. if that's your time slots, and you try listening here, no one is using it, by all means try to send you packets. If anyone is using it for any reason, you don't use it. I'll show you how in full details. Look at this. Imagine that's your actual channel. 4 users are using it. Okay? That's your medium being shared by the 4 users. So how does this look like? Where is the actual data being sent and how it's being sent? Again, let's try to make it, this is your actual channel medium. This is being used by, let's make it easy. Let's make it, say I have 2 users, A and user B. In reality, when you send an actual frame, you send it bounded by time. So we say in this point, which is T0, you figured out to send some information. So in this stage, you started broadcasting your information. This is broadcasted in this way, so it's going to go in that direction towards A. A, at the moment, if he's listening at this time, this is team 0, and this is T2. Okay? That's 2 seconds into the future. Will he detect there is an error, or anyone is using the channel or not? And why? No, why? What is required for the message to arrive to you? What type of, do you remember the delays that we had? We had 4 delays. One of them is what? Which one of the delays that needs you to arrive from a certain point, i.e. a distance, divided by the speed? Which one was that? Propagation. Which does that mean that you are allowed to listen it whenever you receive that frame. So that's your propagation delay. So at this stage, that's T plus 2. There's no one using it, so he started to send at the same time. At this stage, unless he starts to have that conflict of information, then there will happen that collision. Did you understand what happened here? You have the full access and you're trying to listen to the bandwidth, but this will fall into the propagation delay, where you start listening to the actual bandwidth, but there's nothing happening until you reach the stage that you start listening to the packets, and then the packets got lost. So if there's one user, everything is perfect. One user is using it, nothing, there's no issues, and everything one using it at the same time. So B is trying to use it at T0, and he's trying to broadcast his information. At that stage, if B is listening at this stage, he will figure out there is a collision, but he waited until T1 to start sending his information. So the only issue with carrier sense multiplier access is you will fall into the delay of the propagation. That's the only thing. It will be beneficial from a side where it will not have any collision if you are listening properly, but you'll end up with a propagation delay, and that's one of the disadvantages. But is much better compared to the channel partitioning and the 2 first slots of the Aloha one. Is that clear what happened here? The carrier sense multiplier access.
Does that mean that message would get dropped?
Until this stage, until now everything is going past perfectly. Until that, start dropping the packets because they are going into collision. And you end up in this stage, he stopped transmitting and this one could pass. So imagine it as packets. Those are actually packets being passed. Whenever there is a collision, those packets start dropping. Until a stage where one of them stopped sending, then the collision will disappear. So people are saying this is not even better than the previous ones. How do I avoid this? You need to have something over it called collision detection in order to avoid everything. So collision can still occur because of the propagation delay, which means 2 nodes may not hear each other transmission. A collision, entire packet of transmission will have a time wasted. So all of those packets, that's bounded by time, will be wasted. So we need to have some mechanism of detecting that error. At the moment there's no detection. You leave it as it is until one of you stops sending. So they created a part where you have a collision detection. So in other words, you need to detect, abort the sending, and wait for the other guy to finish. The carrier sensing differ as a carrier sense multiplier access with a collision detection. A colliding transmission aborted would reduce a channel wastage. So the only thing you've added here, you have a collision detection, where whenever you detect that detection of an actual collision, you stop sending. That's it. Okay, how will that happen? By the way, this is easy in wired lines, which measure the single of strength of the compare transmitted between the receiver signals. But it's difficult in wireless, which is very, very logical. With wired communication, you have a higher speed, better understanding of the whole medium, which is easy for you to detect the sending and receiving of the actual frame. But with actual wireless, the propagation delay will be higher, and therefore you might end up with a larger collision compared to the wired ones. So, similar to the first example, we'll just look at the first one to remember. This is still continuing, the error is still continuing, the conflict of the information is still happening, no one is stopping until one of you just stop sending your packets. In the collision detection, whenever a user detects a collision has started, they stop sending. So they detect and then abort to control the wastage of the actual channel. Is that clear? How will that be controlled? So how long will that depend on what you can detect the actual collision? Distance and distance divided by speed, i.e. in other words, the propagation delay. That's how it's depending on. As long as the delay of the propagation is less than normal, then you can detect it as fast as you can. Any questions? Is it clear? No?
No.
What's not clear?
The collision.
Sorry?
Collision.
The collision itself? That's your channel. If you have a channel being used by everyone, okay? Let's make it to packets rather than an actual figure. Let's say A and B. Let's have C in there. So this is your time. Let's say this is your time, and you can send depending on your time limits. So you say A is trying to send information at T0. Is that okay? So when you send information, this is sent this way. In reality, this is how it's sent. This is how you occupy your actual channel. What's this? This is your packets. This is your actual packets. How long will C detect there is actual collision? So let's say this is T0, T1, T2, T3, T4. How long it will take for it to detect? That stage, is it? Which is, let's say, T2. Is that right? So it actually, until that stage, all those packets are passing by perfectly. There's no issue. So let's say this guy he's listening. Nothing is happening. So at the same time at T0, he's trying to send information. At T1, if he's transmitting at T1, there's no collision because he hasn't heard there's anything at the actual channel. He will hear only at T2. So if he tried to transmit at T1, and a collision will occur. If he waited until T2, he can listen there is an actual happening, an actual send of information from A is happening. That's still not clear. So that's the time, that's the propagation delay. The question is, even if an actual collision occurred, when will that stop? That will stop whenever you detect an error has occurred. You say you are sending information here at T1, and everything is fine, but you try to detect at this moment. You stop sending information. And therefore, the actual wastage of the channel will be less. That's the collision detection. So channel partitioning is share the channel efficiently and fairly at high load. It's inefficient at low load whereby delay of the channel will be divided by the bandwidth. The random access is efficient at low load, but single node can fully utilize the channel. And high load collision, there is an overhead. So, what do we need to achieve? We need to achieve the best of both worlds. Because the first one, there's no collision whatsoever. The second one, you can use the full channel, but there will be a collision if both of you start sending at the same time. The third one is the ideal one, where you have taking turns. You have the full channel, you allow someone to send or not. So let's have a look at the taking turns. First of all, we have pulling, where you have a master node controlling all the slave nodes. What does that mean? That means if I have a pull information, I send it to one of those nodes and ask that node to transfer the data. So now you are controlling it by that master node. Whenever you have a full channel as well, in a series connection, where you have, let's say, user A controlling 5 users. B, C, D, let's say 3 users. And therefore you are connected to a series bus. If you send that pull information to B, that node can send at that time. When that data is sent, B can send the pull again to a different node, and that node can send information. Simple as that. So the master node invites slave nodes to transmit intent, typically used with the dumb slave devices. The concerns are what? And why are there concerns? First of all, you create what? Overhead. What does that overhead mean? That pooling, you're asking people to transmit actual packets, will create overhead, because that's dependent on you as a master node. You send tickets. Okay, now it's your time to transfer. Your time to transfer. How that will create overhead. That's creating messages between those nodes to transmit between the users. You'll have latency. What's latency? What's latency? In network terminology, what's that?
Delay.
Delay. So, as a master node, you're controlling the actual environment where you ask nodes to send. But if it's all bounded by you, for example, if I'm the master node and I'm trying to be biased to B, and I'm sending him all the cards and I'm waiting those to be waiting for his information. Or at least, he's having a large packet of information to upload. Meanwhile, you just want to upload a simple picture to Facebook. Meanwhile, he wants to upload a 4K video to YouTube. How is this fair? So now, here you have a delay. So yes, it's okay, you're using the full bandwidth. And yes, there's no collision, but there's no fairness. You have a latency there. You have a delay of the user just waiting. Is he finished? That's how simple it is. Single point of failure. If this failed, everything will stop. If A just has a bug inside the machine, you cannot use it. Simple as that. You drop, everything will drop. Again, is this better? In my opinion, it's much better than the first two, taking turns. Is it clear? That one, compared to the first two. There's another part of it called token passive. Rather than have it in a series bus, you'll have it in a ring token, where you control the passing of information by that token card. Very similar to what you call it, the pooling. But in here, you'll ask, do you have anything to send? Rather than giving you a specific amount of time or the full data to send, you ask the person what exactly you are sending and how long it takes you to send. Therefore, you're controlling the actual network better rather than leaving it in a series bus, in the pooling one. So this one will be different, and you're controlling the sending towards the people who have better sending of information with control of time. Sorry. That's the only difference. So you have a token. You send that token to a user. If he has something to send, fair enough. If not, he'll say nothing to send. He'll send the ticket to other people. So that ticket will be passed by a user to other users. But there will be issues as well. First of all, if you are a greedy node, we have a term in networking called greedy user, where you take the ticket and you hold. I'll say, I'm not sending anything now, but I'm waiting until I have some information to send. That's you. What would that create? Delay. Simple. But that happens. That happens in vehicle networks. In vehicle networks, it's the same. We depend on nodes to pass information to other nodes. So if you have 3 cars moving and an application for us, for example, we're trying to implement at the moment with one of my PhD students who's implementing a safety application with ambulance, where whenever an ambulance is coming in, rather than having a siren sending it, you want to send information to other users. We have an issue where greedy nodes don't want to send the information. Take the packet and sit on it. I'm not sending that. Why? I don't care. So either he's a malicious node, or either he don't want to consume any of his bandwidth. So how do you control that? Again, there are some policies related to it, but that's a greedy node. It happens at this, what do you call it, a taking turns, or a token passing. It creates overhead as well, because you're controlling it with a token card, rather than leaving it random to other users to send. That's creates overhead. And again, it's a circle connection, a single point of failure as well. Same old problem with the first one. So summary of those three. A channel partitioning is dividing the partition of the actual shared medium into either by time or frequency. We have the third one called the cold one, but we haven't described it at the moment. Random access is dynamic, but has more collision issues. We have defined three of those: Aloha, Pure Aloha, and the CSMA. Where you have used, the CSMA is used with the wireless connection and wired, the collision detection with Ethernet, and with the 802 there's an avoidance one. I haven't described it today, so don't need to worry about it. Taking turns are pulling from a central stir or a token passing, and the Bluetooth, we use a token ring as well. Okay, I'm stopping early today. Have a break, so we can finish today. I have time, 10 slides of Ethernet, I'll leave it to the next lecture. Okay, thank you for your time.
To use this in a torrent,
Sorry?
it's similar network as a torrent. So you wait until someone's got the data.
Yeah.
This is similar to that.
Yes, similar to the actual.
As long as you got the CDAs, you can do the data.
Yeah, you can transfer the data. Okay?